Hello everyone. Today I want to share a simulation of the high velocity impacts of silicon carbide. And here is the result. And I will show you the impact process. The left viewport shows the damage parameters of the part, and the right viewport shows the kinetic energy decreases as the process. So I can show you the animation. And the time is 7 microseconds. And the silicon carbide is brittle material, and we used the Dragon the DP model. And at the end of the simulation, we can see the penetration dips here, and it's about 17 millimeter. Okay. It's in the y direction, so it's about 28 millimeters. Oh, sorry. It should be 15 millimeter. From the counter plot, we can measure the penetration depths of this high velocity impacts. Here is the ductile damage parameter, and also we can see the effective plastic strain or the stresses. And the stress is large enough so to see the count plots clearly, I will make it a limit here. Then we can see the stress count plot clearly. This is the stress distribution when the penetration occurred. And the projectile is gold material and has defined the shear damage parameters. So the tip of the projectile is failed and the elements have been deleted. We can see here. So then let me show you how to create this model and get this result. So first of all, we can see here there are two parts in this model. The first is the projectile and the second is the target. And this one is the projectile. It's a long rod made of gold. And here is a part of cylinder target. What it is made of silicon carbide. And the element is is very thin and the number is large enough, so we can get a better result. And then we define the two materials, and the first is gold. Here we define a ductile damage, and the fracture strength is 0.2, and the damage evolution parameters. Here we don't give any value for the fracture energy, so when the fracture strength reaches 0.2, the element will be deleted. And also the density, elastic. The elastic, here we define it with the shear modular, and shear modular is 27.2 gigapascal. And also we have defined the equation of states for the gold material, and this is the 3 parameters. And for the silicon carbide material, we define the density, and the plastic model we have applied the Drucker-Prague model, and here is the parameters and hardening parameter. The compression yield stress and damage parameter. Also ductile damage, and we have defined a curve of fracture strength vs stress thresholdy. So this is a curve, and we can save it fracture, and later I'll see it in the result. So here is the material model of the two material, and then we need to create the section for these two parts, and because they are also all solid elements, we just define the solid homogeneous section for the two parts, and then we assign the section property to this part. We can see we have assigned the section property and also the projectile. Here, material is gold. Then we go to the assembly module and adjust the position of the parts, and it's not difficult. Then we enter the interaction module. Here we need to create contact interaction because the impact occurred. So here we use general contact and defined a surface pair. The surface pair is here. We need to choose the element inside the surface. So when the element is deleted, and the new element surface will show up and create the contact. And the contact property, we just give it a default contact property. So after we created the interaction, we can go to the load module. Here we need to create the boundary condition and initial velocity of the projectile. So the boundary condition here we define with the velocity, because these are the symmetry faces. So we need to constrain the velocity, and we need a cylinder coordinate system here. And here there are 10 boundary conditions here. And I will show you everyone. Here is the first is the tip of the target, and we give it a velocity of 0 in the y direction. And here is the bottom surface of the target, and here we constrain the v3 velocity. Here we define the transform coordinate system we created. So this v3 is in the z direction. It means the surface can't have velocity in the z direction. And then is the projectile, and v1 constraint here is in the x direction. Also in the z direction. So along this axis, all the nodes just have velocity in the negative y direction. So the other two directions, the velocity are 0. So here is the velocity in the circum direction, and we define the coordinate system we created, and also the other side. The v2, v1 is in the r direction, and v2 is the circumtangent direction. And then here is the target axis nodes, and it has 0 velocity in all three directions. But for the symmetric surface, we need to constrain the velocity in perpendicular the surface. So here we used the transform coordinate system we created, and also for the opposite side here. So this is the boundary condition for this model, and then we need to create an initial velocity for the projectile, and the initial velocity is about 4,000 meters per second. So here we need to choose all the elements of the projectile and give it a translational only velocity. And here is the one negative direction, and the value is 4,000 meters per second. And this is true high velocity impact. After all this has done, we can create a mesh, because the mesh is imported into the model, so it's all from mesh, or you can create them yourself. And the element size is fine enough, and we can see the element size is about 0.008. It's about 8 micrometers, and the element type is C3D8 reduced element, and all the elements we need to define the element deletion. So here element deletion we need to check, then okay. Also for the target part we need also check the element deletion option. So it's after all of this we check the output. So the first we check the U and V output field put, and the second one we define the damage criteria and effective plastic strain and stress and status. Here the status is indicate the element if is active, and this yeah, and the history output we just keep it as default, and then we can create a job and submit it, and this model will take a long time for my computer. It's about, let me see, it take my computer about 8 hours for this model. So because the time is 7 microseconds, and we don't use a mass scaling, so it take longer time. After the job is completed, we can check the results, and here we can see the stress, and oh, I have gave it limit, so I can see the displacement, elastic strain, and effective plastic strain, and the damage variable. So this is all about today's tutorial of high velocity impact of silicon carbide. So if you like to learn ABAQUS AE or simulation, please subscribe my channel, and thank you for watching.